All right, let's just jump right in. We are about to unpack one of the most brilliant, most delicate, and I mean truly audacious experiments in the entire history of science. It's a quest to do something that sounds totally impossible, using a machine of almost ghostly precision.
No, I mean, really. Just think about that for a second. How would you even begin to weigh the entire planet? The ground under your feet, all the oceans, all the mountains, the super hot core, everything. It sounds less like a real scientific question and more like, I don't know, a riddle from some ancient myth, right?
But back in the 1700s, this wasn't just some fun thought experiment. For the top scientists of the day, it was a huge, gaping hole in what they knew about the universe. I mean, they'd figured out how big the Earth was, they had its circumference down pretty well, but they had absolutely no clue how massive it was. Not a clue.
So what was the holdup? Why was this so ridiculously hard to figure out? Well, the problem isn't the Earth's gravity. Obviously, that's super strong. It's holding us all down right now. No, the real problem is that gravity, when you look at it on a smaller, more human scale, is just unbelievably weak, like almost impossible to even measure.
And this, right here, is the absolute heart of the challenge. See, the pull of the entire planet is what keeps you in your chair. But what about the gravitational pull between two regular objects? Let's say two bowling balls sitting next to each other. That force is so faint that it just gets drowned out by everything else. Air currents, vibrations, you name it. So if you're going to weigh the Earth, you first have to find a way to measure that tiny whisper of a force.
So how in the world did they pull it off? The answer is just ingenious. It lies in this incredible, astonishingly sensitive device. And this thing has a fascinating story all its own. This was a machine literally built to hear gravity's whisper.
So the first person to come up with this brilliant idea was a guy named John Michell. He didn't just dream it up, he actually built the whole apparatus. But then, in a really tragic twist, he died before he ever got the chance to run the experiment. So the machine, this incredible invention, was passed on. And it ended up in the hands of a brilliant and famously shy scientist named Henry Cavendish. And he was the one who would finally finish the job. And this is the star of the show, the torsion balance. You know, the concept behind it is just beautifully simple. Imagine you hang a little rod from a really thin wire. Even the teeniest little push on that rod will make the wire twist. So if you can measure how much it twists, you can measure the force that pushed it. Simple, right? But so powerful.
Okay, so here's the basic setup. You've got this delicate little dumbbell, right? Two small lead balls on a rod, and the whole thing is hanging from that thin wire. Then, you bring two huge lead weights up close to the small ones. And what happens? The tiny gravitational pull between the big balls and the small balls, well, it actually pulls the dumbbell, making it rotate just a little bit. That tiny angle that the wire twists, that's the key. That's everything.
Now look, having the machine is one thing, but actually using it, that's a whole other ball game. Henry Cavendish, the lengths he went to were just unbelievable. He had to completely isolate his experiment from the rest of the world, just to be sure he was only measuring one thing, the pure, unadulterated force of gravity. His dedication was just next level. The entire machine was housed inside a giant mahogany box, almost 2 meters wide, just to block any tiny air currents. And that box, it was inside a closed shed on his property. And get this, Cavendish himself wasn't even in the room when he ran the experiment. Nope, he watched the whole thing through telescopes he'd stuck through holes in the shed wall because he was worried his own body heat might mess up the results. That's how precise he had to be.
So to get that gravitational pull he needed, he used these two absolutely massive lead balls. We're talking 158 kilograms times each. That's about 348 pounds apiece. These were the heavyweights in his delicate little cosmic dance.
And the force that these huge weights actually exerted, it was, well, it's almost impossible to imagine how small it was. We're talking 1.74 times 10 to the -7 newtons. Okay, to put that into perspective, that's about 1/50 millionths of the weight of the little balls themselves. It's just mind-bogglingly tiny, a truly ghostly force.
So, all that work, the shed, the box, the telescopes, the massive weights, it all came down to measuring a movement of just about 4 millimeters. That's it, less than 1/4 of an inch. The entire success of this world-changing experiment hinged on measuring that tiny little twitch.
And here's where it gets just stunning.
Using these special rulers called vernier scales and peering through his telescopes, Cavendish was able to measure that tiny movement with an accuracy of better than 1/4 of a millimeter. I mean, think about that. This wasn't just good for the 1700s. This was a total game changer. It proved that you could measure the fundamental forces of the universe, no matter how ridiculously faint they were. You could capture them.
So, okay, after all that painstaking work, what did he find? What was the big reveal? What did he get from this absolutely monumental effort?
Okay, now here's something really important to understand. Cavendish didn't actually write down the mass of the Earth in kilograms. That's not how he thought about it. Instead, he calculated its density. He figured out how much denser the Earth was compared to, of all things, water. So in a way, he was literally weighing the world against a bucket of water.
And just look at this result. I mean, get ready for this. Back in 1798, in a shed, with a device he basically put together himself, Cavendish calculated that the Earth is 5.448 times denser than water. The modern accepted value we use today, 5.514. It's just unreal.
That is just jaw-dropping. His number, from over 200 years ago, was off by only 1%. It's maybe one of the greatest testaments to careful, meticulous scientific work ever.
And here's a great little fun fact for you. In his original paper, Cavendish actually made a tiny math error, so the number he published was a little different. It took until 1821 for another scientist to go back, rerun the numbers, and realize that Cavendish's actual data was even more accurate than Cavendish himself thought it was. How cool is that?
But wait, the story doesn't even end there, because the real, lasting legacy of this experiment goes way beyond just getting the weight of our planet right. It ended up giving us one of the most fundamental numbers in all of physics, a number that describes the whole universe.
You know, it's pretty fascinating when you remember that the way people talked about physics was totally different back then. Cavendish never once mentioned Big G, the universal gravitational constant that we all learn about in school today. That whole idea, it wasn't really a thing yet. For him, the grand prize, the whole point of the experiment, was figuring out the Earth's density.
Actually, it took a whole 75 years after his experiment for scientists to formally introduce Big G into the laws of gravity. And that's why Cavendish never calculated it himself. It wasn't part of the scientific world he lived in.
So what happened was, scientists who came later took his unbelievably accurate data and they used it to do the first ever real calculation of G. His measurements, made in that shed, became the bedrock for figuring out a universal constant, a number that dictates how planets move, how stars are born, and how galaxies hold together across the entire cosmos.
And that leaves us with one last kind of wild thought. Even with all of our amazing technology today, lasers, atomic clocks, you name it, Big G is still one of the hardest fundamental constants to measure accurately. It's notoriously tricky. Which really makes you stop and think, doesn't it? What kind of special genius did it take to nail it down so perfectly in a drafty shed over 200 years ago?